Number 10. The galaxy without dark matter. On March 28, 2018, astronomer Peter Van Dokkum and his team at Yale University announced a discovery that shouldn't exist. Using the custom-built Dragonfly telephoto array, they had identified NGC 1052-DF2, a galaxy approximately 65 million light-years away that appeared to contain virtually no dark matter. This was unprecedented. Every galaxy ever observed in the universe contains roughly 85% dark matter by mass, the invisible substance that holds galaxies together and dominates cosmic structure. Van Dokkum's team measured the velocities of 10 globular clusters orbiting the galaxy, expecting to find the characteristic signatures of dark matter's gravitational influence. Instead, they found something unsettling. The clusters moved slowly, their velocities suggesting the galaxy's mass came entirely from visible stars. There was no dark matter halo, no invisible scaffolding that every model of galaxy formation requires. The discovery was revolutionary, paradoxically both challenging dark matter theory while simultaneously supporting it. If dark matter and normal matter can be separated, it proves dark matter exists as a distinct substance rather than being an illusion of modified gravity. But then came the controversy. In October 2019, astronomer Ignacio Trujillo published a reanalysis using Hubble Space Telescope data, concluding the galaxy was only 42 million light-years away, not 65 million. At this closer distance, the cluster velocities would imply normal amounts of dark matter. The galaxy would be unremarkable. Van Dokkum defended his distance measurement. Multiple follow-up studies produced conflicting results. The debate continues 6 years later. What makes this particularly unsettling is the fundamental uncertainty. The most revolutionary galaxy discovery in decades hinges entirely on a distance measurement astronomers can't agree on. If it's far, it rewrites galaxy formation theory. If it's close, it's just another galaxy, and we've spent 6 years arguing over a measurement error. Sometimes the biggest mysteries in space aren't what we've found, but whether we've actually found it at all. Number 9. Betelgeuse's unpredictable death. In late 2019, something unprecedented happened to one of the night sky's most famous stars. Betelgeuse, the red supergiant marking Orion's right shoulder, began dimming rapidly. By February 2020, it had faded to roughly 36% of its normal brightness, dropping from the 10th brightest star visible from Earth to barely making the top 20. Astronomers worldwide watch with a mixture of excitement and concern. Betelgeuse is a star in its death throes, expected to explode as a supernova within the next 100,000 years. Was this the beginning of the end? The dimming was unlike anything recorded in over 2 centuries of observation. Betelgeuse is a known variable star, its brightness fluctuating in overlapping cycles of roughly 420 and 2,200 days. But this plunge exceeded all previous variability by a significant margin. Amateur astronomers could see the difference with their naked eyes. Interferometric images from the Very Large Telescope revealed the dimming was asymmetric, concentrated on the star's southern hemisphere, appearing as a vast dark region on its face. By April 2020, Betelgeuse recovered to normal brightness. A year later, the explanation emerged. The star had ejected a massive blob of material from its surface, which cooled in space and formed an optically thick dust cloud, temporarily blocking our view. The mechanism was understood. Crisis averted, except it wasn't. In late 2023, Betelgeuse surprised astronomers again by becoming unusually bright, exceeding its normal maximum. The star continues to behave unpredictably, defying the pulsation models that should govern its behavior. What makes this truly unsettling isn't what happened in 2020, but what it revealed about our ignorance. We can measure stars thousands of light years away with exquisite precision, map their surface features, analyze their chemistry, yet we cannot predict when they will die or how they will behave in their final century. Betelgeuse will explode someday, perhaps tomorrow, perhaps in 100,000 years. Despite all our technology and all our models, we have absolutely no idea when. The countdown has already begun and we're completely blind to how much time remains. Number 8. The Cosmic Microwave Background Cold Spot. In 2004, NASA's Wilkinson Microwave Anisotropy Probe delivered a map of the oldest light in the universe, the cosmic microwave background radiation left over from the Big Bang itself. Among the expected tiny temperature fluctuations, typically just 18 microkelvins above or below the average, astronomers found something that shouldn't exist. An enormous region in the constellation Eridanus, spanning roughly 70 degrees of sky that was approximately 70 microkelvins colder than its surroundings. The ESA's Planck satellite confirmed it in 2013. The cold spot was real. What makes this feature particularly troubling is its size and its implications. According to standard inflationary cosmology, fluctuations this large and this cold should be extraordinarily rare, occurring perhaps once in 50 random random universe realizations. The cold spot has relatively sharp edges rather than gradual transitions, suggesting a specific cause rather than random fluctuation. In 2015, astronomer Istvan Shapudi discovered a supervoid, an underdense region roughly 1.8 billion light-years across, aligned with the cold spot's direction. Photons from the cosmic microwave background lose energy climbing out of such voids through the integrated Sachs-Wolf effect, creating cold spots and temperature maps. But here's the problem. Even this giant void accounts for only 30% of the observed temperature deficit. Something else is needed to explain the full effect. The remaining explanations venture into unsettling territory. It could be a statistical fluke, the cosmic equivalent of flipping 10 coins and getting 10 heads. Or it could be a topological defect, a scar from a phase transition in the early universe. Most provocatively, some cosmologists, including Laura Mersini-Houghton, have proposed it might be evidence of a collision between our universe and another universe before cosmic inflation, a bruise left on the fabric of space-time itself. If the cold spot is a multiverse collision imprint, we're not looking at an anomaly within our universe, but at evidence that other universes exist beyond our cosmic horizon. The oldest light in the universe might be showing us the boundary where our reality touched another, a cosmic fossil of an encounter that preceded everything we know. Number 7. The Proxima Centauri signal. On April 29th, 2019, the Parkes Radio Telescope in Australia was conducting routine observations of Proxima Centauri, our nearest stellar neighbor, at just 4.2 light-years away, when it detected something extraordinary. A narrowband radio signal at 982.002 MHz appeared in the data, lasting for several hours across multiple observation sessions. The signal only manifested when the telescope pointed directly at Proxima Centauri. When pointed elsewhere, it vanished. This directional dependence is the fundamental test for distinguishing cosmic sources from terrestrial interference. What made this signal, designated BLC1 by the Breakthrough Listen team, so compelling was its behavior. The frequency was unusually specific, not matching common interference sources like satellites or aircraft. It exhibited Doppler drift at approximately 0.5 Hz per second, consistent with a transmitter on a rotating planet. The drift direction changed appropriately between observation sessions, exactly as expected if the source were in the Proxima system. Proxima Centauri hosts at least 2 planets, including Proxima b, an Earth-mass world in the habitable zone. Undergraduate student Shane Smith, reviewing the data months later, recognized that BLC1 had passed more interference filters than any candidate signal in decades. The discovery remained secret until December 2020, when news leaked to the press. By October 2021, the Breakthrough Listen team published their comprehensive analysis. Their conclusion: most likely human-generated interference, though the exact source was never definitively identified. Follow-up observations detected nothing. The signal has never repeated despite extensive searching. Analysis of the full dataset revealed 4 million other narrowband signals, most clearly local interference, suggesting BLC1 belonged to this population despite its unusual properties. Yet uncertainty lingers. The specific piece of equipment or mechanism that generated the signal remains unidentified. Its behavior was sophisticated enough to mimic an extraterrestrial transmission in ways that typical interference doesn't, whether alien beacon or terrestrial artifact. BLC1 demonstrated that even our most advanced protocols can encounter candidates that resist conclusive explanation, leaving us with ambiguity where we desperately want certainty. Number 6. The mysterious 3.5 kiloelectron-volt X-ray line. In February 2014, 2 independent research teams published papers almost simultaneously, each reporting the same impossible discovery. Ezra Bulbul at the Harvard-Smithsonian Center for Astrophysics, analyzing data from NASA's Chandra X-ray Observatory, had detected an X-ray emission line at 3.5 kiloelectron volts in the Perseus galaxy cluster. On the same day, Alexei Boyarsky at Leiden University published findings from the XMM Newton telescope showing the identical signal in multiple galaxy clusters and in the Andromeda galaxy. The problem was immediate and profound. No known atomic transition produces X-rays at this energy. Every element's X-ray emissions have been cataloged with exquisite precision. Physicists know exactly which energies correspond to which atomic processes. 3.5 kiloelectron volts matches nothing. It's not potassium at 3.3, not sulfur at 2.5, not argon at 3.1. No combination of known emission lines produces this signal, yet there it was, appearing consistently across different objects, observed by different instruments, always in regions expected to contain large amounts of dark matter. The leading explanation ventures into territory physicists have sought for decades: sterile neutrinos, hypothetical particles that could constitute dark matter. If sterile neutrinos with a mass of 7 kiloelectron volts exist, they would occasionally decay into a normal neutrino plus a photon carrying exactly 3.5 kiloelectron volts of energy. This would be the first direct detection of dark matter particles, solving one of physics' greatest mysteries. centuries. But a decade later, the signal remains at the edge of detectability. Japan's Hitomi satellite with superior resolution observed Perseus in 2016 and found no clear line at the expected intensity before the mission failed. Some follow-up observations confirm the signal, others find nothing. The exact energy varies slightly between analyses, from 3.48 to 3.52 kiloelectron volts, raising questions about whether it's even a single phenomenon. After 10 years, astronomers still cannot answer the most basic question: is the signal real? And if it is, what produces X-rays at an energy that nothing in our understanding of atomic physics can explain? Number 5. The missing neighbor. On January 20th, 2016, astronomers Konstantin Batygin and Michael E. Brown published a paper proposing something almost embarrassing. A major planet exists in our solar system that we've never seen. Their evidence wasn't direct observation, but rather the peculiar behavior of distant objects beyond Neptune. 6 trans-Neptunian objects with extreme orbits, all with semi-major axes, greater than 250 astronomical units, showed orbital clustering that had only a 0.7% probability of occurring randomly. Their arguments of perihelion aligned, their longitudes of ascending node clustered, their orbital planes tilted in similar directions. Computer simulations provided compelling support. When researchers included a hypothetical planet of 5 to 10 Earth masses in a distant tilted orbit averaging roughly 600 astronomical units from the Sun, the simulations perfectly reproduced the observed clustering. The planet's gravity would naturally shepherd these distant objects into the precise configuration we observe. Without such a planet, the orbits should be randomly distributed. They're not. The historical precedent is striking. In 1846, astronomers discovered Neptune through exactly this method, predicting its position from perturbations in Uranus's orbit before telescopes confirmed it within 1 degree of the calculated location. Planet 9 would represent history repeating a hidden massive world, shaping solar system dynamics for billions of years, while remaining invisible. Yet extensive searches have found nothing. As of 2024, approximately 80% of the predicted orbital parameter space has been eliminated by surveys. The Subaru telescope, the Dark Energy Survey, and other wide-field programs have systematically searched vast regions of sky at the brightness levels Planet 9 should possess. Either it exists in the remaining 20% of unsearched space, likely in the southern sky near aphelion where it would be faintest, or the statistical clustering is an extraordinary coincidence created by observational bias, and we've spent a decade chasing phantom gravitational effects that don't exist. After centuries of solar system exploration, we face an uncomfortable possibility. We might not know how many planets orbit our own star. Number 4. Phosphine in Venus's clouds. On September 14th, 2020, astronomer Jane Greaves and her international team announced a discovery that ignited one of astronomy's fiercest controversies. Using the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile, they had detected phosphine gas in Venus's atmosphere at altitudes between 53 and 61 kilometers, precisely where temperatures hover around 30 degrees Celsius, theoretically survivable for microbial life. The concentration was approximately 20 parts per billion, later revised to 1 to 4 parts per billion after reanalysis disputes. What makes this detection so troubling is what phosphine represents. On Earth, this molecule is primarily produced by anaerobic bacteria in oxygen-free environments, or by industrial processes. It's a biomarker associated with life, but Venus should destroy phosphine almost instantly. The planet's atmosphere is 96% carbon dioxide with clouds of sulfuric acid. Ultraviolet radiation and atmospheric chemistry should break down phosphine within hours. Yet, if the detection is real, something is continuously producing roughly 10,000 tons of the gas to maintain observed levels. Every proposed non-biological explanation fails spectacularly. Volcanism, lightning, meteorite delivery, photochemical reactions. Scientists have calculated each mechanism's potential phosphine production. All fall short by factors of 10,000 or more. The chemistry simply doesn't work. Either Venus harbors life in its clouds, floating microbes that have adapted to sulfuric acid and produce phosphine as a metabolic byproduct, or there's atmospheric chemistry occurring on our neighboring planet that contradicts everything we understand about how molecules behave. The controversy deepened when some researchers disputed the detection itself, claiming the signal might be sulfur dioxide misidentified or a data processing artifact. Multiple reanalyses have produced conflicting results. Some confirm the phosphine, others find nothing. After 4 years, scientists cannot even agree on whether the molecule is actually there. If it is, we've potentially found life. If it isn't, we've spent years chasing a ghost in the data. Either way, something is profoundly wrong with our understanding. Number 3. The periodic fast radio burst. burst. On September 16, 2018, the Canadian Hydrogen Intensity Mapping Experiment Telescope detected a fast radio burst from roughly 500 million light-years away. These millisecond-long explosions of radio energy are among the most powerful phenomena in the universe, releasing as much energy as the sun produces in decades, compressed into a time span shorter than a heartbeat. FRB 180916 was initially unremarkable, just another addition to the growing catalog. Then astronomers noticed something that defied every theoretical model. It was repeating with clockwork precision. The burst became active for approximately 4 to 5 days, producing multiple radio flashes during this window. Then it went completely silent for 12 days. Then the cycle repeated. 16.35 days. Over and over with a precision that has remained stable for years of continuous observation. This is the only fast radio burst discovered with such regular periodicity, and no astrophysical mechanism adequately explains it. Neutron stars rotate in milliseconds to seconds, far too fast. White dwarfs spin in seconds to hours, still too fast. Binary star systems could have 16-day orbital periods, but creating the active quiet window pattern requires geometries that don't naturally explain why bursts occur sporadically, even during the active phase. Some models propose a neutron star orbiting a massive companion whose stellar wind periodically blocks our view, but the details don't quite work. Precession of a neutron star's magnetic field could create beamed emission we only see periodically, but neutron star precession typically operates on timescales of years, not weeks. What makes this particularly unsettling is the active window behavior. Why does the source burst for 4 days, then maintain perfect radio silence for 12? It suggests external modulation, some mechanism turning the emission on and off with extraordinary regularity. The phenomenon has revealed that fast radio bursts are far more diverse than we imagined, and somewhere in that diversity lies physics we haven't discovered yet. Number 2, our solar system's tilt. There's a fundamental property of our solar system that astronomers have known about for decades, but never adequately explained. The sun's equator is tilted 6 degrees relative to the plane in which the planets orbit. This shouldn't happen. The solar system formed from a rotating disk of gas and dust 4.6 billion years ago. As this disk collapsed, conservation of angular momentum dictated that everything should rotate in the same plane. The planets do, more or less, their orbits aligned within a few degrees of each other, but the sun itself rotates at an angle, as if something torqued the entire system off its original axis. For centuries, this 6-degree tilt remained an unexplained quirk, an anomaly noted in textbooks but never satisfactorily resolved. Then in 2016, when Konstantin Batygin and Michael Brown proposed Planet 9 to explain the clustering of distant trans-Neptunian objects, they realized their hypothetical planet solved another mystery simultaneously. Computer simulations showed that a massive planet in a tilted orbit, slowly precessing over billions of years, would gravitationally influence the plane in which other bodies orbit. Over the age of the solar system, this influence would accumulate, gradually tilting the orbital plane of everything interior to the planet, while leaving the sun's original rotation axis unchanged. The result? A 6-degree misalignment, exactly what we observed. The physics is straightforward and elegant. The implications are unsettling. If this explanation is correct, our solar system's most basic geometric property, the arrangement that defines the ecliptic plane and governs planetary motion, has been shaped for its entire existence by an object we've never seen. Every orbit, every season, every astronomical alignment has been influenced by this hidden massive world. We live in a planetary system whose fundamental architecture is controlled by something lurking beyond our ability to detect it, something that has been there all along, pulling strings from the darkness beyond Neptune. Number 1, the Hubble Tension. In 2019, cosmologists declared a crisis. 2 independent, equally precise, equally credible methods for measuring the universe's expansion rate were giving answers that didn't match, and the discrepancy was getting worse as measurements improved, not better. This shouldn't be possible. When scientists refined their measurements, values should converge. Instead, they were diverging, the gap widening with each advancement in observational technology. The Planck satellite measured the cosmic microwave background, analyzing the universe as it appeared 380,000 years after the Big Bang. From this ancient light, cosmologists calculated the Hubble constant, the universe's expansion rate, at approximately 67 kilometers per second per megaparsec. Meanwhile, Adam Riess, who won the Nobel Prize for discovering that the universe's expansion is accelerating, led a team using the Hubble Space Telescope to measure the expansion rate locally, observing Cepheid variable stars and Type Ia supernovae within several 100 million light years. Their result? Approximately 73 kilometers per second per megaparsec. 9% doesn't sound catastrophic until you understand what it means. Both measurements have been checked exhaustively. Both teams have eliminated every systematic error they can imagine. Both methods are considered fundamentally sound. The statistical significance reached 5 sigma in 2021, a 1 in 3.5 million chance of being random coincidence. This level of disagreement suggests something is fundamentally broken in our cosmological model. Either there's unknown physics operating between the early universe and now, dark energy's properties are changing over time. New particles exist that we haven't discovered, or one of our most trusted measurement techniques contains a systematic error that has eluded detection despite years of scrutiny. The implications extend beyond academic curiosity. Our entire understanding of the universe's composition, age, and fate depends on knowing the expansion rate accurately. We've built a cosmological model where dark energy constitutes 68% of everything that exists, dark matter another 27%, and normal matter just 5%. These numbers come from measurements that assume we understand the expansion rate. If we're wrong about the Hubble constant, we're potentially wrong about the fundamental makeup of reality. What makes the Hubble tension truly unsettling is its persistence. This isn't a flash-in-the-pan anomaly or a controversial claim by a fringe researcher. This is a systematic, reproducible, increasingly significant discrepancy between two of cosmology's most important measurements, acknowledged by the entire astronomical community. For over a decade, the best minds in physics have been unable to resolve it. Better data has made the problem worse. Something about our universe, something fundamental, is wrong in our models. And despite all our technology, all our mathematics, all our theoretical frameworks, we cannot figure out what it is. We stand at a crossroads where one of two things must be true. Either we're making a subtle mistake we can't identify, or the universe is trying to tell us that everything we think we know about its expansion, its composition, and its ultimate fate needs to be reconsidered from the ground up. If you want to see more videos like this, click the video on screen now and make sure to subscribe.